Well, welcome quantum mechanics students to our first online lecture. I know you're all excited. It's definitely been harder than what I expected. So let's see, we're going to review the square well scattering. We're going to review scattering from a potential step, and actually not a step, but a potential rise. And then last we'll look at tunneling through a potential step, or basically a square barrier. So let's just review what we had going on with this problem. We were just near the end at our last class. Our wave function in the first region was composed of free particle wave functions, e to the I k1x plus b e to the minus I k1x, where recall that the wave number k1 involves the energy. It's the square root of 2me over h bar squared. Right, so in this region here. In region 2, a little bit different. The energy is different, right? Because you have the kinetic energy of the particles, but you also have a non-zero, a negative potential energy. So that still has free particle wave functions, but we have a different wave number because we have a different energy. It's minus I k2x. Here k2 is the square root of 2m e plus v0 over h bar squared. All right, in region 3, we allow for only particles moving to the right, because particles would have to be incident from the right moving left to have any free particles moving left. Has the same wave number as region 1 because the energy is the same. So we give it a K1. Okay, you apply boundary conditions, right? Remember those boundary conditions. What I'm going to do is just cut to the chase here. So apply boundary conditions. And do a lot of algebra. I can quickly summarize. We get rid of the B part. Well, we basically want to see how the transmission occurs. If we wanted to see how the scattering, the backwards scattering waves are, we would solve for B. But instead, we eliminate B and we eliminate C. It's found, we don't eliminate C. It's found that your C value looks like this. In terms of right, the width of our well is A, that's why it's appearing here. So that was C. C and F, we'll talk about the transmission essentially. D was found to be quite similar, 1/2, 1 minus, K1 over K2, and F e to the sum of these wave numbers. Messing around with those, we eventually got A in terms of F. We had A. It was an ugly mess. I'll never forget doing it because it took so much work. F over 4 e to the I k1a times 4 cosine of k2a minus 2I times k2 over k1 plus k1 over k2 sine of k2a. Recall, transmission coefficient is essentially the ratio of F over A, right? A is how much is coming in, F is how much eventually goes out, leaving the potential well. T was defined as the transmitted flux over the incident flux, value F squared, and basically this was the velocity, right? K1 h bar over m. It's the velocity in region 3 and region 1. And then we have our a squared k1h over m as well. Those cancel, and you're left with essentially, well, I'll write it like this. F over A modulus square. Looking at this right here, we see that F over A is going to be an ugly mess, so it's a little bit easier to mess with 1 over T, but that's just algebra. So as we skip to the end, we find that the transmission coefficient is this very interesting function here. It goes like 1 plus 1/4 V0 squared over E times E plus V0 squared. No square. And right there, this is an important factor, sine squared of K2A. Now, from that, we realize sine can be 0 or 1 or minus 1. Sine squared can only be 0 or 1, right? This oscillates back and forth between 0 and 1. When it's 0, boom, t equals 1. When it's 1, t is some smaller value, right? So when sine of K2A equals 0, or K2A is an integer multiple of pi, right? N is an integer. Well, then we can actually find the energy. But what's most important is when transmission coefficient equals 1. And all particles are transmitted. There's no reflection. Which is a pretty interesting result, but only under this circumstance. And so we sort of investigate a little bit as to what that means under that circumstance. All right, I'll save that. I'm going to go back. So what I'm going to do is just jump back to my previous result. Oops, I worry. It just changed it. Great. Here's how I will fix this. Well, I guess I won't. So we'll just go blank and remember what our setup looks like. So here's our square well scattering. Page 2. So we were in the situation here where we had that K2A had to equal n pi, where n is an integer, etc. But what is k? Recall, k2 was our square root of 2m e plus v0 over h bar squared. Right? So what we're going to do is use this result and go ahead and input. Oh, and I can. No, I can't select it all. I'll have to ragdoll that. 2m e plus v0 over h bar squared. That's equal to an integer multiple of pi. Well, go do your math and let's solve for e. Okay, well, first thing, let's square both sides, bring the a over. We're going to have 2m e plus v0 over h bar squared equal to n squared pi squared over a squared. And then multiply both sides by h bar squared, divide both sides by 2m, and we'll be left with e plus v0 equal to n squared, n squared h bar squared pi squared over 2m a squared. Continue on with our work here and solve for e. What I'm going to do is write out h bar in terms of h over 2 pi, so we have something more familiar. So it's h squared over 4 pi squared instead of h bar squared, and that's times pi squared over 2m a squared minus v0. Last, the result we have for the energies, and this is when we have perfect transmission. Our energies, well, let's see, the h squared, the 4 comes down here as an 8, the pi squareds cancel. You get n squared h squared over 8m a squared, which is just like a particle in a box, but minus our v0 value. And again, this is for n equal 1, 2, 3, with a transmission coefficient equals 1. So that's a pretty interesting result. When t equals 1, we call those transmission resonances. And for particular values of energy, the particles will have no problem. They won't be scattered at all. Pretty interesting result.